Okay, so this is homework number 2, problem 2. And so for the first part, we're asked to plot the function f of x is equal to 1 minus e to the negative alpha x times u of x minus c. So u of x minus c is just the unit step function, and the unit step function is equal to 1 when x is positive and equal to 0 when x is negative. So x minus c is simply just the unit step function shifted to the right by c. And 1 minus e to the negative alpha x is simply just this below. So when you multiply the two, any value before c is equal to 0 in the unit step function. So when you multiply 0 times this function, this also becomes 0. So you effectively truncate before c, the function, and then after c, it's just the normal function of 1 minus e to the negative alpha x. And this height is equal to when x equals to c, so it's equal to 1 minus e to the negative alpha c. So this is big F of x. So in the second part, we're asked to find the probability density function from big F of x and to prove whether or not it is a valid density function. So in order to have a valid density function, the integral over the bounds has to equal 1. So in order to take the derivative of big F of x, we simply just apply chain rule. So it's the first part times the derivative of the second part plus the derivative of the first part times the second part. So here we take the derivative of the first part, so it just becomes the alpha goes out in front, the negative alpha cancels with the negative in front, so it just becomes alpha e to the negative alpha x times the unit step function plus 1 minus e to the negative alpha x times the derivative of the unit step function, which is the impulse function. And so the impulse function is simply just is equal to infinity during that point, and it's 0 elsewhere. And it also has effectively no width, but infinite height. And so the graph of this would simply just look like this. You have the impulse function, and then after the impulse function, it just becomes the function of alpha e to the negative alpha x. So an important thing we have to do in order to integrate this function is that we have to apply this property of impulses. And the property is that h of x times the impulse of x minus a is equal to h of a times the impulse function of x of a. So after we make that change, 1 minus e to the negative alpha x becomes 1 minus e to the negative alpha c. So this is important when we start integrating. So when we integrate small f of x, we have this part, and we can split up the integration by integrate the first part and integrating the second part. So when we integrate the first part, it's simply just instead of going from negative infinity to infinity, it's just from c to infinity, because that's when the function exists. And when you take the integrate of that, it just becomes negative e to negative alpha x between c and infinity. But the second part, because we switched the x equal to c, this is effectively a constant. So this can come out of the equation, and it becomes the integral of the impulse function. The integral of the impulse function is equal to 1. So it's 1 times 1 minus e to the negative alpha c. And that is the area of this impulse function. So then when we take the first part from c to infinity, we get a negative e to the negative alpha c. That becomes a positive e to the alpha c plus 1 minus e to the negative alpha c. The e to the negative alpha c's cancel out, and we get 1, which validates the probability density function.